Hi everyone, Mr. Lee here. In this video, we're going to go over rotational kinematics. Alright, so rotational kinematics, the name implies that there's a little bit of kinematics involved, and there's also things that move it around in a circle, hence rotational and then kinematics. So if you remember, kinematics is the study of motion. So now we're going to study how the spinning objects, right, and like why things spin and how they spin and how we can really look at a spinning object and put it into a formulaic form. Now I'm going to break this down into two parts. The first part is all going to be about the equations slash variables. And the next part, I want to focus on the graphical nature of it. Because if you remember from the kinematics unit, we did a lot of graphical things, and the same is true, especially for rotational kinematics. All right, let's begin. So the first part I want to start off is with the equations. Now, I'm actually going to start off with the variables for regular linear kinematics. Okay. So we have x for position, we have v for velocity, I guess I should write this down, position, v for velocity, we have a for acceleration, and we have t for time. Now, even though you know this, I do suggest that you write this down because it really helps with the next part. Before we do that, let's write the units. M for position for meters, velocity is meters per second, acceleration is meters per second, aka meters per second squared, and of course time is second. So you can kind of see like this cascading effect, right, of how we go from one variable to the next. Meters per second squared, and then of course seconds. All right, so this is what we call the linear kinematics, or the non-rotational stuff. Okay, now let's do the rotational kinematics. All right, now the hardest part of rotational kinematics, in my personal opinion, is getting used to the variables. Okay, because up until here we did a lot of we used the alphabet that we know. Okay, so this is I guess the romantic version of the alphabet. But now we are going to be using the Greek form of the alphabet, or the Greek variables. So instead of saying x for position, we're going to say theta. Okay, theta. Now what I'm going to do is I'm going to write the pronunciation as well as what it represents. So this is theta. This is something that you might know because we use theta when we talk about angles, but you know it comes up again. So theta is the angular or the rotational. Okay, so you might hear me say this back and forth, angular / rotational position. Okay, so it's where we are along basically the circle. Next, instead of v for velocity, we are going to say omega. Now, sometimes you might see me write it like a very squiggly W. Sometimes it might just look like a W, but this is omega. Okay, and this represents the rotational or / angular, I'm just going to say rotational here on out, rotational velocity is less to right. Okay. Next, we have acceleration. Now, be careful here because this acceleration, it's an A, and the Greek form, it looks a lot like an A, but kind of looks like a fish. Okay, fishy. So this is alpha. Okay, alpha the fish, and this represents our rotational acceleration. Okay, it's so if the velocity tells you how fast something is spinning, so how fast it is rotating / spinning, okay, rotational acceleration is how much it is speeding up / slowing down. Now, I'm gonna do this in red, right? So this is one of those star kind of moments. You need to know this. It does not tell you how fast something is moving, because that is velocity. This is acceleration. It just tells you the change in velocity. Okay, all right. I'll write that down. Is the change in velocity. All right, this is very important. much like over here, I'll write this underneath. The acceleration is the change in velocity, not how fast something is moving. And the reason why I'm bringing this up again and again is because this is something that a lot of students forget. Because they think, oh, if something has a very high acceleration, it must be moving fast. That's not the case, right? So that's very important there. And the last one, of course, time. Now, what do you think is rotational time? Right? You might think, well, of course, Mr. Lee, that's easy. Rotational time is just the face of a clock. Jokes. It's just T for time. All right. Now for the units. Now I'm going to do the units, I guess, on the left-hand side, and I was getting a little messy on the right-hand side. So the units for theta, we're going to use radians, R-A-D. Now, please do not confuse radians with radius. Okay, radius is the distance from the center to the outside part of the rotating object. Radian is the unit for angular position, and we're following a trend here, right? Meters radians, therefore angular velocity is radians per second. And then we have radians per second, aka radians per second squared. And the unit for rotational time is just seconds. All right, so here are the variables. And you'll see that it lines up. It's very analogous. Just because the object is rotating, it doesn't like give it like an extra special meaning. We just have a different variable for it. Right? Now, with that, we can come across the kinematics equations. So the three kinematics equations that you'll see on the AP1 exam. So we have VF is equal to VO plus the acceleration times the time. Okay. We have VF squared is equal to V initial squared plus 2 times A times the displacement. Okay. And then we have X of F is equal to X of O plus V initial times time plus 1/2 times the acceleration times the time squared. So we have these three big major equations. Okay, so what we're going to do is we're going to use the chart that you have above. I know you can't really see it on my screen, so I'll just scroll that a little down right there, and we're going to come up with the kinematics equations for the rotational kinematics. Okay, so the three. So instead of saying V sub F, we go over to our chart and we say, okay, instead of saying V for velocity, we can say omega. Okay, because it's analogous, it's the same thing. So we can say omega final is equal to omega initial, right, because V and V, plus, so instead of saying A for acceleration, we look at a chart and we say that it's alpha. Now, I do want you to get used to using the proper terminology. Because that is, well, one, that's how we communicate, but it really does make a difference. Like in your brain, you're thinking, okay, if I'm using the words alpha, if I'm using the words theta, if I'm using the words omega, I know I'm talking about rotating objects. Okay, it just kind of like just sets everything in place. So this is our very first equation. The next, we have VF squared. So instead of saying V for velocity, we look at a chart and we say, okay, V is analogous to omega. So we say omega final squared is equal to, instead of saying V initial squared, we can say omega initial squared plus 2 times, instead of saying A for acceleration, we look at a chart and we say, oh, okay, instead of saying A, we can say alpha times the change in position. And our change in position is our theta. So that's equation number 2. All right, now let's finish this off. So instead of saying X for position, we see that it's theta. So we say it's theta F is equal to theta initial, because X and X, plus, instead of saying V initial for velocity, we can say that it is omega initial times the time plus 1/2, instead of saying A for acceleration, we say alpha, and then time squared. So here are our three rotational kinematics equations. Now, from here, we can also come up with the different definitions for the different variables. So, for example, we know that velocity is equal to, so if we take a look at this third equation over here, right, this third equation, we can say that the change in position, so what I'm doing is I'm moving X of O over to the other side. We're saying that acceleration is 0, so we get change in position divided by the change in time, right? So this is displacement over time for velocity. and that is something we do cover, right? And one way to really check yourself is to see what the units are. So we know that the units for position is meters, the units for time is seconds, so we should look at that. The units for velocity is meters per second, so we could use the same technique for omega, right? Omega is the change in theta over the change in time, and we have radians per second. Okay, and then we know that acceleration is the change in velocity over the change in time. So we get meters per second, and that just gives us meters per second squared, right? Right, so just gonna write that on the side. And alpha is the same. It'll be the change in omega over the change in time, and we get, of course, radians per second divided by seconds, and that gives us radians per second squared. Okay, so here we have our the intro. I like to call them the intro equations. From there, if you remember the kinematics units, we went from these two equations to these three, but kind of went in reverse this time. All right, so that's how you can identify the rotational kinematics equations. Make sure you have these down because this is what we're going to be using from here on out whenever we do our practice problems. Okay, so the next thing I want to do is I want to focus on the graphical nature of things. Now, once again, I'm going to start off just as a brief little intro, the kinematics version that we're pretty good with. Okay, all right. So when we take a look at the graphical stuff, I don't like to use these three major equations because that all requires an acceleration. I want to focus on the two intro equations here. So if I have a position versus time graph, right? So if I have a position versus time graph, I take a look here at this equation right here, right? So this is a position versus time. I can see that if I have a line, the slope for a position versus time graph is my velocity, and that is one of those memorizing kind of things. You need to know this, right? We know that the slope is velocity because slope, remember, is the division, aka the rise over the run, and our rise is x and our run is t. All right. Now, if you don't have this down by now in our physics career, you got to just memorize this. You know, put it on your bed, put it on your mirror, look at it every day. You need to know this one. All right. Okay. So equivalent. The equivalent would be the theta versus time. So if we have theta versus time, the units for theta, of course, are radians. The units for time, of course, seconds. Therefore, the slope. This would be omega, okay, for the same reason, because slope is rise over run. Our rise is theta, check, and our run is time, check. So I'm just looking at this basic equation and I'm kind of like translating it into graphical form, right? I'm looking at it, I'm like, all right, so what is our y-axis, what is our x-axis, and how do those variables match our graphs? All right. So the next thing that we have to do is we have to be able to identify, all right, so we know that here this is a positive slope, therefore we have a positive velocity, right? Now we should also be able to identify, I'm going to do this in a different color so that you can see a little bit clearly. If we have like a flat line, so what this means is that you have a constant velocity. Okay, so this velocity is zero, right? Like, because there's no slope. There's no slope. All right, next up we have, I'm going to do red here. So we have something like this. If it's going down, because that's a negative slope, this would be a negative velocity. All right. Okay, so from there we can go to a velocity time graph. So if we have a velocity time graph, we take a look at our equations and we say, okay, so this equation right here has velocity and time, and then we have acceleration. So because velocity and time, those are our y and our x axes, and they're dividing, we can see that the slope is the acceleration. Once again, it's the whole idea of rise over run of velocity divided by the time. All right, so next we can translate that into the rotational version. So instead of having v for velocity, we have omega for velocity, and then we have t for time, and therefore if we have a sloping line like this, this will represent not a for acceleration, but alpha for rotational acceleration. Okay, and I'll go through the three again. So this one gives us a positive acceleration. If it's flat like this, oh boy, that's not really flat, is it? All right, let me try my best. There we go. So this gives us an acceleration of 0. and I'm going to do my last one in red. This gives us a negative acceleration, okay? And it's all about like the slope. You know, is it going up? Is it flat? Is it going down? Okay, all right. So from there, we can, when we originally studied this, we looked at the different kinds of graphs, and we'll go over that right now. Okay, so here we have the two different versions of the graphs that you might see, but on the exam, what they really like to do is they like to really try to push your knowledge about these kinds of things. And so, like, you know, students are really used to seeing like a position time graph, a velocity time graph, but you know, you throw in those Greek letters and then like things get a little bit trickier. And so I do want to showcase that because there's a higher chance that you'll see the Greek versions of it. All right, I'm going to go to a little spot where I have a little bit more space. Okay, so let's do a theta versus time graph. I'm going to put that x-axis right in the middle, actually. Okay, so we have a theta versus time graph. All right, so before I'm even looking at this, I'm thinking to myself, all right, the slope, what does the slope represent? Okay, so that's the very first thing. The slope represents the velocity, right? And so what I like to do is I like to actually write it down in the linear form, and then I like to translate it into the rotational form. Only because like my brain doesn't work with Greek letters, right? I like to go from one form to the other. I like to take it step by step. So if we have something that looks like this, boom. Okay, so here we can see that this is not a constant slope, right? The slope is changing, and so we can take a look at this and be like, all right, well, how can we analyze this? The slope is not the same, so we can say omega is changing. C-H-A-N-G-I-N-G. Okay, so what we can say is we have a delta omega. And once again, if you're not used to the Greek letters yet, just above it, write the linear version, we have delta v. So if we have delta v, that must mean that we have a acceleration. Okay, so that must mean we must have an acceleration, which is our alpha. So if I take a look at this, how I want you to observe it is the two major parts. So the two major parts for this graph is, I'm going to highlight it. The first major part is down there at the beginning, and the second major part, I'm going to do this in a different color, is at the end. Okay, so I'm going to write up myself a little note. Here we have a slope that is flat. Okay, so if my slope is flat, I just have to replace the word slope with omega, my velocity. My velocity is 0. Okay, so I'm not moving in the beginning. This object is not spinning. But here I have a positive slope. Okay, so, and it's like pretty steep, so it's going pretty fast compared to, like, let's say the middle part, and I'll highlight that. I don't want to focus too much on it, but I do want to show you like why this end is more steeper than this. So this part right here, I'm gonna do this in red, like that's the slope, and this one's like basically vertical. Okay, so we go from no velocity to a positive slope. So that must mean the object is speeding up. Now, if you remember, we had this giant chart where we can say, okay, so if our velocity and our acceleration, they have the same signs, the object is speeding up. If they have different signs, then that means that the object is slowing down. So for this case, if I were to create a chart, I would say that my omega, my velocity, and my alpha, okay, I have a positive velocity at the end. Oh my gosh. And therefore my alpha is also positive. Okay, so I have a positive acceleration here. All right, now because I said I was going to finish the chart, this is representative of this graph, so I'll show you a different one. Okay, I'm not going to go too much in depth. I do want to do a more cursory version of this, so a little bit quicker, right? So if I had something that looks like this, boom. Right? I want to look at my two major parts. I'm going to get out my highlighter to showcase. I'm looking at this initial part, and I want to take a look at this final part right here. All right, so I can see here I have a slope of 0, so my omega is 0. I'm not moving. Right here I have a pretty big omega actually, and that is negative. So I went from not moving to moving, but in the negative direction. So that could just mean like it's spinning in the opposite direction of whatever you consider to be positive. Okay, all right, so here we can say that omega is negative and our alpha therefore was also negative, okay, because that's why it was speeding up. All right, so we have two of those versions. Let's do another one. We have omega versus time, and let's do something like this. All right, look at that. So this is a reverse version of what we've been seeing. Okay, I want to look at the end, and of course, I want to look at the beginning. All right, so the beginning we have a very oops, this should be, excuse me. This should be a theta. All right, so this is theta, and so my slope here, I have a very negative slope, and here we kind of flatten it out, right? We have no velocity. So we were moving and then we slowed down. So this means that we slowed down. All right. Now, if I have my chart, we have omega and we have alpha. I start off with a negative velocity, and remember, if you're slowing down, your two signs have to be opposite. Therefore, I have a positive acceleration. Okay, so that's just one example. And there are many different iterations, but my strategy will always be the same for each one of those situations. Identify the first part and the last part, okay, and see what the slope is going from one part to another. And from there, you can really make your predictions as to what's going on here. All right, so the last thing I want to go over before I wrap up this video is the area under the curve. Okay, and in order to do area under the curve, let's focus on the equation. Here we have velocity is equal to displacement divided by the time. Now remember, area under the curve is a multiplication looking thing, right? And so if I'm multiplying things, I'm multiplying in this equation here, velocity times time is equal to the displacement. So that right there, the velocity times the time, that is your area on the curve. These are my axes, and therefore my area on the curve represents the displacement. So what that would look like, right? And remember what I said, the velocity and the time, those are my multiplying things, therefore they are my axes. So I have a velocity times time graph, right? And if I have, let's say, something that looks like this, okay, this, I'm gonna highlight this middle, or make it red, right? This area under the curve. Okay, if I were to ask you, what does that represent? You could tell me that represents my displacement. Okay, and so the same also goes for anything that's rotational. So setting velocity is equal to displacement divided by time. We can say omega is equal to delta theta divided by delta time. Okay, if I'm multiplying the variables, I have omega times delta t is equal to delta theta, right? And once again, because these two are the things that I'm multiplying, these are my axes, and this is my area under the curve. So do a omega times time, okay? And so if I have, I'm gonna create a different shape for y'all, right? So I have something that looks like this, right? So that must mean that this area under the curve right there, that is my, I'm gonna make that better. This is my, I'm gonna make a, that is my displacement, right? Because that is my area under the curve, right? And the other version of this, just to get a good roundabout feeling about it, so we did a velocity graph. We also, so can we do anything else? I think that's it. Oh yeah, so we can also do the acceleration version. So I'm going to skip the linear version. I'm going to go straight into the rotational version. So we know that alpha is equal to delta omega over delta time. Okay, if I'm multiplying the variables, I have alpha times delta t, and remember alpha means acceleration, is equal to the change in omega, also known as the velocity. And same strategy, okay? These are the two variables that I'm multiplying. Therefore, these are my axes, and this is the product. Therefore, this is my area under the curve. And so if I have a alpha time graph, and I don't know, I'm gonna do something like that. I change it up on us, right? So I have something that looks like this. Then my area under the curve, I'm gonna use blue for this one. Okay, this area and that area under the curve. If I add those two up, this will give me my delta omega, which is my velocity, my change in velocity, my change in rotational velocity. All right, now let's do a quick review. Rotational velocity is just like regular kinematics, except we have now Greek letters, and all of the rules still apply, including the stuff with graphical information. And so if you still have your notes from back then, it will definitely help you out. Now at first, your head might be spinning, because we're using Greek letters, but don't let that deter you. It just takes a little bit getting used to, and if you find yourself having a little bit more difficult time getting used to the Greek letters in your brain, go step by step. First, determine what it is in the linear fashion, in the linear kinematics, and then from there, translate it into the Greek letters, aka the rotational stuff. All right, I'll see you next time. Bye-bye.